So, hello to everyone who's watching on YouTube. Maybe let's wait for like 10-15 minutes before we get started. So, just waiting for a few people to join the session in person. So, if no one else joins in the like next say next 10-15 minutes, we'll get started nonetheless. So, I'll mute myself till then. Okay, so it seems that no one has joined the session in person. So, anyways, we can get started. So, yeah. First of all, sorry. First of all, hello to everyone. I'm Lakshya. So sorry, my camera is not working today due to some technical issues. So I'm Lakshya Sagi, the problem-solving TA for the NPTEL special topics in algorithms course, and this is going to be our last session, which is supposed to be the summary session. So in this session, we'll be more, like we don't have any problems to discuss. It's not a problem-solving session, as I described in our last session also, but this is more of a summary session where I'll try to summarize all of the concepts which were covered in the lecture videos over the course of 12 weeks. So you can think of this like this video as a more of a revision video for you guys. So yeah, and yeah, this will be the last time we'll be meeting at least for this semester. So yeah. So also I remember okay, so maybe I'll just share my screen so that we can get started with the summary session. And I'll just tell you guys about the plan for today. Okay. Uh, Let me just share my screen. Yeah. So I hope my screen is visible to everyone. So this week actually, since it's a summary section, we have to go over topics on a very high level which were covered over all the weeks. Note that this is of course not a substitute for all the lectures because like how much can I even go over in 2 hours of the whole, which was the topics which are covered over 14 weeks. But this will be more of a very quick revision. Uh, but also I realized that also I remember that we did not have any sessions for week one and week two course contents uh, because of certain scheduling conflicts. We did not have any sessions for week one and week two. So I decided that maybe we can have first more in-depth revision for the week one and week two contents because we did not discuss them in any of the sessions. So we'll have so even though it's a summary session, a lot of the focus will be on the contents for week one and week two. And then we'll be just so almost half of the time of the session will be spent on the contents of week one and week two. And then for the remaining time, whatever is left, we'll try to on a very high level just go over all the topics which we have uh, done for uh, the other weeks. So yeah. So let's just get started. Discussed in what was discussed in week one? Uh, so essentially in first week and also the second week we started out with uh, some basic graph algorithms, like not basic but yeah a bit advanced graph algorithms. And the first problem which was discussed was the network flow problem. So what is the network flow problem? So suppose we are given a directed graph G, which has vertices and edges, and there's a capacity function on the edges. Like so, every edge has a positive capacity, and we are also given a source x and a sink vertex. Essentially, you can think that these edges as kind of pipes, and these pipes have some kind of capacity that how much water can they carry per minute. And you have a water source and you have a water sink. And now what you have to compute is the maximum amount of flow which goes from source to sink. Essentially, the maximum amount of flow which goes, maximum amount of water which we can pump from source to sink per minute or something like that. So some of the things which a flow will satisfy is these conditions. The flow should satisfy these conditions. One is the capacity constraint that, of course, the flow passing through any edge must be less at most the capacity of that edge because because the flow cannot achieve the capacity of that edge. And another constraint is the flow conservation constraint. Essentially, since the vertex S is the water source and vertex T is the water sink or the flow sink, so none of the other vertices can act as a source or a sink. So whatever amount of flow comes into the other vertices, that amount of flow should exit those vertices. So for any vertex V, which is not S or T, the amount of incoming flow, the flow for all the edges U comma V which are coming into V, should be equal to the amount of outgoing flow. So the flow going out from V to all the vertices W. So these are the two constraints which a flow should always which a flow should satisfy. So any function, so this can be thought of as a function over edges, like which maps like every edge to some real value, like non-negative value, and then you can say that that function is a valid flow function if it respects the capacity constraints as well as these flow conservation constraints. So as an application, why are we even studying this problem? So So yeah, one of the applications is suppose one has to transfer oil from source to sink in a network. Like I said, water, similar thing can be thought of for oil. And yeah, we assume that without loss of generality that there are no anti-parallel edges. And this can be assumed because uh, for any pair of vertices, if there are like a pair of anti-parallel edges, then we can actually break it down into like two edges, like one goes from U to V with capacity C1, and other which goes from, okay, so this should not be from this direction, since C2 is going backward, it should be this direction, like there is an edge from like V to D and then D to U. But yeah, so we can assume that the graph does not have any anti-parallel edges, although it's not really important, but yeah. And also we can assume that there are no parallel edges because if there are two edges which have capacity C1 and C2, we can instead have like a single edge which carries a capacity of C1 plus C2. Yeah. And then the computational task is find F with maximum value. So the mass flow problem essentially says that find the maximum amount of flow which we can send from source to sink. And one naive algorithm which like a lot of people might come up with is okay, like just find some ST path, pump up some flow into that path, then the remaining graph again find another ST path and then pump up some flow in the other path also. But there is an issue in the naive algorithm because as we can see, consider this is the graph. So the source is a sink and these are the edge capacities. Then suppose I initially choose this path, the S to A to B to T path in the naive algorithm. Then since this is the bottleneck edge for this path, this one capacity edge, so at most we can only send one amount of flow through this path. But if we send one amount of flow through this path, then this edge can further only carry one amount of flow. This edge can carry still two amount of flow. This edge can carry further only one amount of flow. This can carry two amounts of flow, right? So now the maximum flow after sending a flow along this path, I can only send a flow of 1 unit further, uh, or like 2 units further. So one flow I can send from here to here, another flow I can send from here to here. Like 1 unit of flow from here to here because this will be a bottleneck edge of capacity 1. Here also this will be a bottleneck edge of capacity 1. So 1 unit of flow can flow from here to here. So overall, I can only send 3 units of flow from source to sink via naive algorithm. But actually, the value of maximum flow in this example is not 3, but instead 4, because you can send 2 units of flow from here to here in the upper path, 2 units from the lower path. So, yeah, so the naive algorithm was just finding any ST path, pump up the flow into that path, then find some other path and pump up the flow is kind of not really a good idea to go about it. But still like there are some things like the algorithm which we will be eventually able to use to solve this problem will somewhat invoke this kind of an idea of finding an SG path, but then we'll also be augmenting edges along these paths. So that will become clearer as we move like uh, to like further discussion. So yeah, so essentially whenever we send a flow, we'll be constructing a residual graph. And this is what is called the Ford-Fulkerson algorithm. So what does the Ford-Fulkerson algorithm say? Uh, so Ford-Fulkerson algorithm says, okay, like just Ford-Fulkerson algorithm just say, like the live algorithm, just send a flow along any path. So just choose any SG path. So just choose this, let's say we choose this blue path. So send the flow along this path, but also don't just fix that, okay, that we have sent the flow across these edges and this is fixed that this amount of flow will be flowing across this path. But rather, let us give us uh, some leeway to like correct if we have chosen some past past path incorrectly. Then let us give us some leeway to correct our mistake, and that can be done by like constructing a residual graph for the network. So what I mean is, suppose you have sent 1 unit of flow from here to here, Then how do we construct a residual graph? So if one so as a residual graph is essentially saying that okay, if an edge from S to A carries a capacity of 1 unit, then uh, an edge from S to A carries a flow of 1 unit, then what we are going to do is we are going to introduce a backward edge which with capacity 1 unit. Essentially, we are saying okay, you have sent a flow along this of 1 unit, but you can send this flow by introducing a backward edge of 1 unit again. So similarly for this part, this edge carries a flow of 1 unit. So the remaining capacity on this forward edge will be 0, but we can introduce a backward edge with capacity 1. For this S to A edge, the forward edge will now have a capacity of 1 because 1 unit has already passed, but we will have a backward edge of capacity 1. And similarly from B to T, we'll have a forward edge of capacity 1 and a backward edge of capacity 1. So this is what the updated graph looks like after sending uh, unit amount of flow. So this is the residual graph after sending 1 unit of flow. And now in this residual graph, one can further send one amount of flow, so we can send a flow along this direction or something, and we can construct some further residual graphs and so on. And actually, it turns out that if you keep constructing these residual graphs and keep sending these flows till you are not able to send any flow through any residual graph, then actually you will obtain what is the maximum flow. And this is what is called the Ford-Fulkerson method. So the algorithm can be written like this. So first initialize f of flow through every edge to be 0, and while there exists an augmenting path from S to T in the residual graph GF, augment f along the path P. So it's essentially like augment the graph and construct the updated residual graph, and keep doing this while there exists an augmenting path, and at the end output uh, the flow f. So yeah. And just to be like, just to formally describe what do we mean by a residual graph? So yeah, so uh, so suppose there's a so this f function denotes the flow passing through any edge, and capacity was the original capacities of the edges in the graph. So in the residual graph GF, we'll have a capacity function CF, which says that okay, for any edge from U to V, uh, the capacity will be nothing but C of u comma v minus flow already passed through the edge u comma v. So in the forward edge, we'll have this amount of capacity this amount of flow can be further sent along the forward direction. But also since we are allowing us to correct our past mistakes, we'll also have a backward edge, and in that backward edge, in the direction v comma u, we'll have a flow of uh, we'll have an edge of capacity f of v comma u, and otherwise the CF function is 0. So yeah. So for every edge, we'll have a forward edge and a backward. So for every edge corresponding in the original graph, we'll have a corresponding forward as well as a backward edge in the residual graph. And the capacities of those edges can be given by this CF function. So yeah. And how do we augment the flow? So augmenting a flow is nothing but so suppose f is already a flow in G and f prime is a flow in GF, then we can just construct new flow function, which is what we call the augmented flow function, which is nothing but for any edge u comma v, uh, just uh, 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 add the f prime function, or like the flow passing through the f prime u comma v value to the original f comma u v value, and subtract the f prime v comma u value, and this is how you can obtain the uh, augmented flow. And with respect to this, you can again construct the residual graph and so on. So this is pretty simple because like if we are just saying that okay, like so if an edge was if an edge was carrying, let's say, a flow of like value f in the forward direction, and the flow in the flow f prime, the edge carries a value of like f prime u comma v in the forward direction. So when both of these flows are added, then both of these flow values should be uh, added together. However, like if this f prime flow also carries some flow in the backward direction from V to U, then you need to subtract out this flow also, because we are talking about the net flow from going from U to V. So this is what the uh, augmented flow is going to look like. So yeah. So this is a very neat trick, and it was shown in the lecture videos that constructing these kinds of residual graphs helps us obtain the maximum flow. Like from a source to a sink. So yeah, so this is a really interesting and like really important trick. This trick of using residual graphs in the context of like flows. Yeah, and then the issue comes up, okay, you have talked about this trick, but is it correct? Like, does it always terminate? So actually, it can be shown that if all the capacities are integers, then every iteration increases flow by value at least one. So the runtime is, if f star is the maximum flow value in the graph, then also like finding an S2T path in any single iteration just takes order v plus e time. And how many iterations do you take? You take f star iterations, because in every iteration you increase the flow value by one, and like the flow value maximum is f star. So the total time taken is f star times v plus e, which is just f star times e. So if all the capacities are integers, then there is a maximum flow where each edge can also like so like if so so what this means is like if all the capacities are integers, then this algorithm terminates in this much time. And also if these capacities are integers, this also shows that there is a maximum flow where each edge carries only integral flow, because always we are increasing the capacity in terms of integers. So yeah, the max flow will carry an integral flow. There can be fractional flows also, which are maximum flows, but there will always exist at least one flow, which is like integral and maximum, only if the capacities are integers. So, yeah. So this is pretty nice. And also, this was discussed in the lecture videos also. Like this also results in a very, very important result in the context of graph theory, which is called Max-Low-Mincut theorem, which says that uh, the value of the maximum SG flow is actually equal to the size of the minimum SG cut. And what's an SG cut? So it will we'll have a more discussion about this later. But like as it was discussed in the lecture, SG cut is nothing but uh, the number of a collection of edges on whose removal there is no remaining path from S to T. So the min SG cut is just the minimum number of edges required to be deleted from G, so that there is no path from S to T in the graph, in the updated graph after deletion. And this actually shows that the theorem says that the value of any maximum SG flow, the value which we obtain from here, is actually equal to the size of the minimum SG cut. So these two quantities, the SG cut and SG flow quantities, are actually related to each other, which is pretty nice. However, there is some slight, okay, so let's just coming back to the discussion about max flows. So in the max flows, this algorithm which we discussed has a runtime of something like f star times the number of edges. So note that this f star is the maximum amount of flow. So since the capacities are integers, so this is kind of a like a pseudo polynomial time algorithm. This is not actually polynomial time, but rather a pseudo polynomial time algorithm. Uh, and yeah, like what's a pseudo polynomial time algorithm? Like we have already discussed in when we are discussing NP hardness and everything. So it would be good if one can obtain like an algorithm which is like not dependent on this value of f star, or at least not dependent on the like value of this f star linearly. Like like it can have a like log f star dependence or something, but at least not this kind of a direct dependence on f star. And and then comes up the Edmond-Karp method. So note that okay, so first of all, why is this Ford-Fulkerson algorithm really important? So it gives us really a blueprint, like it gives us a very nice blueprint about residual graphs and something. So it says that okay, at any point of time, just choose any S to T path, and if you construct a residual graph with respect to that S to T path, then you can further continue doing these kinds of procedure of selecting any S to T path and like uh, constructing the residual graphs and so on till you are not able to reach T from S any further. So this is what the Ford-Fulkerson algorithm gives us, a very high blueprint that choosing any S to T path will suffice for us to solve the problem. So, but if we try to choose this any S2T path instead of this, we try to choose this S2T path smartly, a bit more smartly, then maybe we can do a better job, and maybe we can obtain uh, uh, algorithms which are much faster. Like if we choose this S2T path very smartly with the graphs, and this, but still this progression like gives us a very high like blueprint of like choose any S2T path and then just construct a residual graph on it. So just the smartness which we have to focus on is like choosing such STD paths such that the number of iterations in which we have to pump the flows has to be uh, as low as possible. And this is where this Edmund Carr method comes into the picture. So what they say is, okay, instead of picking any STD path, just pick an STD path which has the minimum number of edges. So yeah, so not like the minimum shortest path or something, but rather the path with the minimum number of edges. And actually it can be so like like in this graph like an STD path, this is an STD path which has two edges, this path has three edges, this has two edges. So this is the path which you can take which has two edges in the Edmund Clark method to send a flow from S to T. And actually it can be shown so this was discussed in the lectures, so yeah, I'll just talk about the final result, that this algorithm iterates mn times, like number of vertices times number of edges times. So there the maximum number of iterations in the like original Ford Fulkerson algorithm was around f star iterations, uh, but here there are at most v times e iterations. And since each iteration takes just finding out the path, STT path with a number of edges, so each iteration takes just like, so this is just a BFS kind of a thing which we have to try. So each iteration just takes like order of E plus V time, or like just the number of edges time. So total runtime of the algorithm will be like this V times E times like the time taken for one BFS, which is just number of edges. So the runtime for Edmund Carver algorithm will be V times E times E, which is just V times E square. So yeah, so this is a pretty nice improvement because now we don't have any dependence on the value of f star. We just have these dependence on the vertices and the edges. So now this is a polynomial time algorithm, not a pseudo polynomial time algorithm. So it's really good. Yeah. So essentially, and there have been like even further developments on, okay, if instead of choosing the minimum number of edges, we choose like the paths some with some other smart criteria or something, then maybe we can have even further better algorithm and all. So yeah, so there's a load of literature, but like the heart of everything lies on this four-fold cursor algorithm, the concept of residual graphs, and yeah, constructing these residual graphs. So that's why it's a pretty important concept. Okay. And then a bit of properties about these flows. So there was discussion about some properties of these flows. So first of all, there are some definition like what's a path flow. So a path flow is uh, you can think of a path flow as just a flow along an ST path. So a path flow F is a path flow if there exists an ST path D such that flow from the edge U to V is 1 if the edge U to V belongs to the path B, and it is -1 if the edge V to U belongs to the uh, path B. So essentially, what we are saying is yeah. So mm, uh, so if you have an ST path P in the in any graph, then you should be having a flow of 1 on all of these edges, and you should be having a flow of -1 on uh, like on the on like the edges which are in the like opposite direction. Like so, yeah. So if V to U is the path in the path B, like, then you have just a flow of -1. Essentially, this is like we had to describe this in term because like in residual graphs also you can have a path flow. But yeah. And similarly, what's a cycle flow? So cycle flow is again something like which is along a cycle. So if there is a cycle C, such that for any forward edge there is a flow of 1, and for any backward edge there is a flow of -1 and 0 otherwise, then it's called a cycle flow. So in a path flow, you have forward edges as 1 and backward edges -1, but the whole flow is along a path. Whereas in a cycle flow, the whole flow is actually along a cycle, not along a path. And then there's this really, really cool and really important theorem about flows, which is, yeah, which has been discussed in the lectures as well, which is called the flow decomposition theorem. And what does this say? It says that every ST flow can be written as a positive linear combination of at most E number of path and cycle flows. And moreover, the edge U to V appears in at least one path or cycle if and only if the flow from edge U to V is greater than zero. So even keeping this aside, this is a very important statement that like any SG flow can actually be written as a linear combination of at most m number of path and cycle flows. So note that SG flow can have a value of any arbitrary value because capacities are very large. They can be 10,000, 1,000,000, anything. But still, the flow can be still written as at most this many path and cycle flows. So this is a really cool and really important property of the flows. So you can always decompose a flow into paths and cycles. This is what if you have to take one if you have to have one takeaway from this flow decomposition theorem, it would be that any ST flow can be written as a combination of paths as well as cycles. And this is really useful in some applications, like we'll see later on. Yeah. And a collection of these cycle flows is also sometimes called a circulation. And yeah, a circulation can decompose into cycle flows, so no path flow is needed. And if an ST flow F is acyclic, then F can actually be decomposed using just path flows. Because since the flow is acyclic, there do not exist any cycles, so it can just be decomposed using path flows. So yeah, these are just corollaries of this flow decomposition theorem. Okay. So we'll see maybe one use of this flow decomposition theorem to design and so initially we had this Ford Fulkerson algorithm for SG max flows. Then we had this Edmond Karp algorithm, which went along like the shortest number of edges, the path which contains shortest number of edges. Now maybe we can have another idea. Uh, and here this kind of a flow decomposition theorem will also come and help us. So the idea is instead of choosing so Edmund Carr chooses the SG path with many number of edges. But suppose instead of this we choose the instead of this we choose the path which choosing these paths are usually called augmenting paths, these SG paths which we choose. So suppose the idea is for max flow instead of this we choose the fattest augmenting path. And what is we mean by fattest augmenting path? So we choose the SG path in the graph GF which has the highest bottleneck capacity. So of all the edges, the bottleneck capacity for a path is defined by the minimum capacity over all the edges on this path. And yeah, if this because that edge is the bottleneck for this path, because that edge essentially says that you can send at most this much amount of flow through this path. And yeah, so if you want, so essentially what it's saying is in any iteration you want to push as much amount of flow as possible from S to D along a single path. So choose the path with maximum bottleneck capacity. So first of all, one question which comes up is, oh, you're talking about choosing this fattest augmenting path, but can this path even be computed? Like, can you compute the path which has the maximum bottleneck capacity? So can this even be computed in polynomial time? And actually, this was given as a homework exercise, but yeah, it's not too hard to show that the BFS or Dijkstra's algorithm, actually, Dijkstra shortest path algorithm can actually be modified to obtain a like uh, maximum bottleneck capacity path also. So Dijkstra is a greedy algorithm. A similar greedy algorithm can be designed for this maximum bottleneck path also, and it's really not too hard to show. So yeah. But what's the really nice use of this is like so if you are able to send uh, uh, like a flow of maximum bottleneck capacity from S to T, uh, then essentially what you are saying is okay, suppose F star was the value of the maximum flow from S to T in the original graph. Then what you have essentially managed to do is if you have sent a flow of capacity, the maximum bottleneck capacity, then we know that the any max flow from this so this flow from this flow decomposition theorem, we know that any max flow can be written as a linear combination of at most m number of path flows. So what this means is that uh, the path which we have selected in this with the maximum bottleneck capacity uh, will have a capacity or will send a flow of value at least f star by m, where m is the number of edges. because total these m number of paths overall carry like a flow of f star. So there should exist at least one path which carries f star by m amount of flow, and we are selecting the maximum bottleneck capacity path. So it should also select like it should also uh, send at least f star by m amount of flow. So in one iteration, actually, uh, you have sent like 1 by mth fraction of the original flow. So the remaining flow is just f star times 1 minus 1 by m. And in the second iteration, after the second iteration, the remaining flow will be f star times 1 minus 1 by m squared. In third iteration, it will be 1 minus 1 by m cube, and so on. And actually, you can show that in some like logarithmic number, in like e log f star iterations, since if the capacities are integers, uh, this flow will become like 0 or like less than 1. And if it is less than 1 and the capacities are integers, then it is essentially 0. So that's how you actually obtain that if the capacities are integral, then in E log f star iteration using this fattest augmenting path, uh, one can actually solve the Max loop problem. And so if there are E log f star iterations, and each iteration just invokes like some kind of a Dijkstra-like algorithm, which just takes like m plus n log n time. So the runtime is just Uh, yeah, so the runtime is E log f star times like this is not just V log V, it should be like E plus V log V, something like E square times log of f star times log of V is kind of the algorithm's runtime. I think there's a mistake in the exhibit, so this should not be just V log V, but rather E plus V log V, because that's what Dijkstra takes. So yeah. So yeah, so this is something like this already gives us something better than like uh, mm, maybe not better, but yeah, like something comparable to this, which was this was like v times e squared, and here it's like okay, yeah, and here it is like e times v times something like this. Mm, yeah. Um, yeah. So it's still yeah. So this is already so if like so this incorporates a log f star factor which was not in Edmond curve, but it takes away like at least one linear term. Like this is just dependent on e square. The previous or like e times v. The previous Edmond curve was dependent on e square times v. So this is somewhat faster. This fastest augmenting path algorithm. If like log f star v and assume is like finite. So this is really nice that we are able to do this in this kind of a runtime. And yeah, so this invokes this idea that so here like this flow decomposition idea is used because you really need this thing that at most e paths can like yeah, every any SG flow can be written using at most e paths, because only then you can say that in any iteration the maximum bottleneck path decreases the flow by a fraction of at least 1 over e. So yeah, so that's why this is pretty nice, and this is the runtime if you use this fattest augmenting path algorithm. So yeah. And then there was discussion about the concept of maximum bipartite matching. So we have already been familiar with this matchings because we have seen this in like a lot of like sessions and a lot of lecture videos after this week 1 and 2 also. But still, let's just for the sake of like completeness, let's just still discuss them again. So what is maximum bipartite matching? So a matching is just a set of edges which do not share any endpoint, and size of any matching is just the number of edges it contains. And the problem by maximum bipartite matching just asks, given a bipartite graph G, find the uh, find the uh, uh, matching with maximum possible size. Yeah. in a bipartite graph, find the matching with maximum possible size. And actually, it was shown in the lectures that the maximum bipartite matching problem can actually be reduced to the max flow problem. So to solve the maximum bipartite matching, you just need to solve the max flow problem, and you will be done. So yeah. So this was discussed in the lecture video. So we'll skip the proof of this. And then there was discussion about the cut problem. So note that previously we talked about this ST cut. So ST cut was yeah. Uh, where did we talk about? Yeah. So we talked about this ST cut, where I said that ST cut is the set of edges which, when removed, uh, which on whose removal there is no S to T path left in the graph, and minimum ST cut is just this kind of a cut with minimum possible size. But if you're not talking about this specific S and T cut, like you don't want just this S and T, but rather you're talking about a global cut. Like it is also called usually a cut. Um, so a global cut is nothing but like in an undirected given undirected weighted graph, a global cut is just like a partition of vertex set in two sets, like x and v minus x. Or you can think of this as like a collection of edges. A cut is a collection of edges on whose removal the graph becomes disconnected. The original graph G becomes disconnected. Initially, G is a connected, undirected weighted graph, but a set of edges on whose removal G becomes disconnected is called a global cut, which we are discussing here. So in ST cut, just S and T have to become disconnected. Whereas in a global cut, like the graph has to become disconnected. So yeah, yeah. And weight of the cut is nothing but the number of edges going across that cut. So then the computational task is to find a cut with minimum possible weight. So yeah, so to find a cut with minimum possible weight, actually we can again use the Maxlow min cut Maxlow algorithm, because what one can do is uh, yeah, for any edge u comma v in the undirected graph, we can replace it with two directed edges, and uh, so let us just fix any v vertex and define it as a source, and then for all the remaining vertices t, because if the graph becomes disconnected, then let's say v lies on this x side, then at least one of the vertices of the graph must lie on this v minus x side also. And so this cut can again that can then be thought of as, like, suppose here there was a vertex v, here there was a vertex u, then this cut can be thought of as a minimum uv cut. So take v as the source, u as the sink, and try to find the minimum vu cut using Ford-Fulkerson algorithm, and you'll obtain the global min cut. So yeah. So you just take v as any vertex, you fix it to be on the source side, and then check for all the other vertices, like find out the minimum SG cuts for all other vertices, and return the minimum possible value over all such cuts, and that will give you the global minimum cut. So yeah. So in order n max flow calls, one max flow call takes like something whatever time it takes. So in order n max flow calls, n is the number of vertices, because you are calling max flow or like minimum cut subroutine for almost all the vertices of the graph. So you'll have like n number of max flow calls to find the minimum cut, the original graph. So yeah, using n macro calls, you can find a global minimum cut in an undirected graph. And then the runtime is just like v times e square was Edmund Cars runtime, and then there are n number of macro calls, so there's a multiplicative factor of n also. So this becomes like n square e square, which is approximately n to the power 6. Uh, because e can be thought of as order of n square. So this is a polynomial time algorithm, but it is not really that much efficient. So yeah. So, but luckily, nicely, people have discovered, like, okay, like global minimum cut, like we do not need to go through these subroutines of these ST minimum cuts to find, because these are like very expensive runtimes now to find these ST minimum cuts. But rather, we can have even nicer algorithms, and one of the most famous algorithms, which introduce like which popularize, I would say, the use of randomized algorithms, like which popularize the use of randomized algorithms, is this Kargar's algorithm for global mid-cut. Like before this, people use randomization to design algorithms, but I think this was one of the first results which showed like how to use like randomization to solve a very nice problem efficiently. So yeah, so Kargar's algorithm for global min-cut uh, it just says that okay, like while there are at least three vertices in the graph, pick any edge uniformly at random from the set of all edges and merge the endpoints of each, and retain the parallel edges but delete all the self loops. So essentially, like you just keep iterating like this, like take any edge uniformly at random and merge its endpoints. In the remaining graph, again merge the endpoints. Remaining graph, again merge the endpoints, and keep on doing this. And finally, let u and v be the vertices left. Then X is the set of vertices that went into side U. And this is, so the remaining super vertices which are remaining at the end is your like cut. And with high probability, actually, Kargar algorithm, like Kargar showed that the resulting cut, if you repeat this experiment like multiple times, you will obtain actually in one of the times the minimum cut also as the vertex partition. So I believe like it was approximately, we need to run like with, so essentially like in one iteration, like with probability 1 over n square, you can guarantee that I think it was something like this, that with probability 1 over n square, you can guarantee that uh, 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 like this will be a global minimum cut. So if you repeat this something like n square times, you obtain like with high probability that you indeed obtain a global minimum cut. So it was something like this. So the overall, so we repeat this process, I think, n square times, and you will actually obtain in one of the times the global minimum cut with high probability. So the overall runtime is nothing but k times n choose 2 times n square, which is just n to the power 4. Yeah. And also like this also gives us like while analyzing this algorithm and all, like this also gives us that the number of minimum cuts in a graph is at most n choose 2. And why is this the case? Kind of because in any iteration of this algorithm, the set of vertices which we obtain is like minimum cut with probability 1 over n square. So in at most, so like there cannot be more than n square minimum cut if this kind of an iteration gives you like one minimum cut with probability 1 over n square. So like, yeah. So on a very high level, the number of minimum cuts in a graph is at, like, this shows that because of this probability bounds, like this was also like really nice result that, but because of this probability bounds, one can actually obtain that the number of minimum cuts in the graph is at most n square and not more than that, or like n choose 2 to be specific. And like when is the tight example, when it is exactly n choose 2, so just consider a cycle graph. If you have a cycle, you can take any two edges and they will constitute a global minimum cut. Cycle over n vertices, so like n choose 2 is the number of cuts. So this bound is tight for cycle graphs. So this is like a pretty nice algorithm, Karka's algorithm, and it has laid foundations for like further improvements over this. Like using this randomization technique, tools of randomization and all, to design like even more efficient algorithms for global minimum cuts. So yeah. Okay then. After this, yeah. So after this, there were discussions about. Previously we have discussed the context of matchings, but it was for maximum bipartite matching, and there was like it was showing the extra videos that one can reduce maximum bipartite matching to just maximum ST flow problem. But like for non-bipartite graphs, turns out this isn't the case. Like we're not so lucky that like in uh, non-bipartite graphs, actually, or let's say in general graphs, the problem of matching does not reduce to like the problem of ST flows. So yeah, so matching is a set of edges with no edges sharing their endpoints, and maximum bipartite matching can reduce to max flow problem. but this is not true for non-bipartite graph. And here we'll have some uh, other tools which we'll be using to design an algorithm for matchings in non-bipartite matching. Yeah. So here, we'll use a concept of augmenting paths. So suppose we are given a graph G, and M is a matching which is given to us. And then like an augmenting path is kind of a certificate which says that, okay, like how can you guarantee that this matching is the maximum possible matching? Or like you cannot improve the size of this matching. Or like, so, but if an augmenting path exists, so if no augmenting path exists, then actually M is a matching of maximum possible size. We are going to show that. And if there does exist an augmenting path, then actually we can improve the size of the matching, increase the size of the matching using this augmenting path. And what is this augmenting path defined as? Like actually it was also in the lecture videos, like why is this true that existence of augmenting path implies that matching size can be increased, and if there does not exist any augmenting path, then uh, matching size then the given matching is the maximum matching. So why is this the case? Like the proof was in the lectures, but now let's just define what even is this augmenting path before we discuss its properties. So a path from for any so a vertex, let's say first of all we define a vertex to be matched or unmatched. If so, a vertex is matched if like one of its incident edges lies in the matching M, which we are considering, and we call a vertex as exposed or unmatched if it is a non-matched vertex. So with respect to a matching M, we'll call a path as augmenting path if let's say the path consists of the vertices v1 till vl. It is called an augmenting path with respect to a matching M if v1 and vl are exposed vertices, or like these v1 and vl are unmatched vertices, and vi comma vi plus 1 for I equal to 2, 4, 6, 8 all belong to the matching M. Essentially what we are saying is, okay, suppose these black edges are the edges which do not lie in the matching, and these red edges are like the edges of the matching M. Then we are saying that uh, so suppose we are considering the path till v1 till, like let's say here's a vertex v6. Let's say we are considering a path from v1 till v6, and then it's an M alternating path, or like an augmenting path with respect to M. If like let's say v1 is not matched to any vertices, so v1 does not have any red neighbor. Similarly, if v6 also does not have any red neighbor, and the v1 to v6 path is actually alternating between black and red. So since v1 does not have any red neighbor, so it has a black neighbor as v2. Then v2, let's say, has a red neighbor v3. Then v3 has a black neighbor v4. v4 has a red neighbor v5, and v5 has a black neighbor v6. So this is an alternating path, and actually it can be shown that if there exists a alternating path, then the size of matching can indeed be increased. And it's very easy to see here why is this the case. So if this is the alternating path, just switch the red and black edges on this path. So suppose instead of this v2 v3 edge, we add the edge v1 v2 to the matching. So this becomes a black edge, this becomes a red edge, and this is feasible because v1 was previously unmatched, so it can be matched. And v2 still remains matched to at most one vertex, so it has only one red edge as incident edge. Similarly, v3 v4 is a red edge, this is a black edge, and this becomes a red edge. So the size of matching now increases from there were initially two red edges, now it becomes like three red edges. So that's why augmenting along like finding this augmenting path can help us increase the size of the matching. Yeah. So if there exists an M augmenting path, then M is not a maximum matching, and it can also be shown the other way around also, that if M is not a maximum matching, then there will exist an M augmenting path. And the proof of this you can see in the lecture videos, but it's not really too hard. But yeah, we won't be discussing that. So essentially, what one can say is a matching M is a maximum matching if and only if there does not exist any M augmenting path. This gives a very nice characterization for maximum matching. But how do we make use of this observation to find out the maximum matching? So on a very high level, what one can do is, okay, let's just include some edge E in the matching, and let's say, okay, this is the initial matching. And while there exists an M augmenting path, increase the So first find an M augmenting path in the graph G, and yeah, then increase or like augment the size of increase the size of matching along this augmenting path. And while there exists an augmenting path, you do this, and if there does not exist, then you just return the matching which you have obtained till now, and that's the maximum matching. So this gives a very high level nice blueprint, but again, like here also, the non-triviality of the in this blueprint, like another tricky thing in this blueprint is like how do we even find this M augmenting path efficiently or like in polynomial time? And this is where like one of the most wonderful results, or like why am I saying this is one of the most wonderful results? Because like it was one of the uh, first results uh, which talked about like these polynomial time algorithms, like so which is called the Edmonds-Blossom algorithm. So essentially, this finds the maximum matchings in non-biquadratic graphs in polynomial time. And like people are not sure even if we before this result that if we can even obtain such an algorithm in polynomial time. So this was one of the first examples of a polynomial time algorithm shown for a non-trivial problem. So yeah. So like this is considered one of the that's why it's considered one of the milestone results in theoretical computer science, the Edmonds-Blossom algorithm. So what is the Edmonds-Blossom algorithm? Like what even is this blossom? So like the idea of the Edmonds-Blossom algorithm is this only that one has to find M augmenting paths repeatedly. But how does one even find these M augmenting paths? And Edmund showed that this can be done using the concept of blossoms. So what is a blossom? Blossom is nothing but a structure or with respect to a matching, like with respect to a given matching M, one can define blossom as a structure, which is nothing but so if you have an alternating path, like red, so suppose you keep alternating between black and red paths, so black, red, black, red, black, red, and now you try to keep trying to go around and find like if an alternating path exists, and now suppose you come back to this original endpoint. So this is kind of uh, like a blossom. So a blossom is essentially nothing but like a cycle which alternates between black and red edges, except at a specific point at which like only exactly two black edges are incident, and this is connected to a stem of this blossom. Uh, Sometimes it's called this part is called the petal, and this is called the stem, and the whole part is called the blossom or the flower. So yeah. So this is the stem of the flower. So it's so essentially a blossom. So essentially a flower in the Edmund blossom algorithm is nothing but a blossom, which is like an alternating cycle, but like with exactly one pair of edges which do not alternate, which are both black edges, and this vertex to be connected to a stem, which is an alternating path. And Edmund actually showed that like if there exist such blossoms, then the given matching M is a maximum matching in G if and only if you contract this blossom to a super vertex, then also like it should be a maximum matching. And the high level idea for this is okay, like if you connect this uh, if you shrink this into a super vertex and you try to find some alternating paths ahead, then actually inside this super vertex also you can find an alternating path along this direction or along this direction. So yeah, uh, that's how Edmonds Blossom algorithm works, and it tries to find out an M augmenting path. Yeah, and like you keep on so you are like contracting this blossom into smaller sizes, so you'll always like decrease the size of the graph, and so like this algorithm will terminate at some point of time to find an augmenting path. So note that this is just one iteration. Like this whole thing, this blossom thing is just to find one augmenting path in the graph, and once you have obtained the augmenting path, you can augment the matching, and then again do this procedure for the uh, updated matching. So yeah, on a high level, like if one wants to write this algorithm down, so what does this Edmond algorithm say? So it just says that uh, mark all the exposed vertices as even, and uh, if u v is an edge and v is unlabeled, then label v as odd and the mate of v as even. So you can mark these edges as even and odd, like instead of these like marked and unmarked or something. And if u v is an edge and v is labeled even and v belongs to another alternating tree, then we have found an m augmenting path. And like if so, like this is just a formal description of the uh, blossom which we discussed. So you can take a look at this and understand this. But yeah. So essentially, the idea is just this: that you try to find these alternating paths, and once you come to a cycle, you have found actually a blossom, and you can contract this blossom away. So yeah, so this is really nice. And note that this blossom will always be an odd length cycle. Why is this the case? This blossom will always be an odd length cycle because, like as we have seen that, like it consists of alternating paths. So and at one point exactly there is no alternation. So if there are alternating paths, then like these two edges can be paired up. So these are two edges, these are two edges, these are two edges, these are two edges. So till here now we have an even length path, and now the last connecting edge. So and after this even length path, there is exactly one further edge. So the length of a blossom is always odd. So maybe I should add that. The length of a blossom is always odd. So yeah. And that's why these kinds of like, so why did we need blossoms in normal graphs but not in bipartite graphs? Because in bipartite graphs actually, like, so blossoms are actually cycles which are of odd length, right? But bipartite graphs do not have any odd length cycles. They only have even length cycles. And that's why these blossoms do not occur in bipartite graphs. And so these kinds of complications do not even arise in bipartite graphs. And one can just find like these augmenting paths using the flow-based techniques or something. So yeah. So this is pretty nice, and yeah, this is how one can try to find these blossoms. And this was shown in the lectures that yeah, uh, the algorithm performs at most n by 2 augmentation. So this is not too hard to see because in every augmentation the matching size increases by at most 1, and like there are n vertices, so the matching size can anyways be at most n by 2. So and between two augmentations, the algorithm can shrink blossoms at most n by 2 times. And so in any augmentation, uh, the time taken is like a v times e, because the blossoms can be shrunk at most n times, and uh, after each shrinking of the blossom, constructing this alternating tree structure takes order m time. So the whole time of like one augmentation is order m times n, and there are n augmentations, so the total time taken is like now n times mn, which is like n square m. So yeah, so this is how the advanced blossom algorithm works. Okay then, so yeah. So this also like I talked about previously about these odd length cycles and even in cycles, like in bipartite graph there is only even length cycle. In non-bipartite graph there is odd length cycles which create these blossom structures and causes a bit more difficulty or a bit more non-trivialness in the problem. So actually yeah, this can also be kind of so in like also like in bipartite graphs we have the or maximum matching we have that Hall's theorem, if you have heard about Hall's theorem, like which says that for any set S, if the size of neighborhood of S is always at least as big as size of S, then we will always have a perfect matching. Or similarly, the size of maximum matching can also be characterized using Hall set. So, and that can be proved using these augmenting paths in bipartite graphs. But can a similar thing be proven to characterize the size of maximum matching in a non-bipartite graph? So can we have an equivalent of Hall's theorem for non-bipartite graphs also? And indeed, like one can, this was shown in the lectures also, by looking at this analysis using these blossoms and everything, one can also actually obtain such a characterization for the size of maximum matching in non-bipartite graphs as well, which is called the Tooth-Birch theorem as well. But maybe let's just take what's given now. Like, let's just discuss this from start. So, like, we won't be going to the proof of this, but what does this even mean? Let's just see. So, suppose we are given a like non-bipartite graph or any general graph. Then consider any set of vertices u in that graph. So suppose you delete all these vertices u, then there will be like some connected components in the remaining graph. Like maybe the graph may get disconnected, but there will be some connected components of this graph, right? And some of the components may have odd number of vertices, some of the components may have even number of vertices. Then actually, like if you're talking about like matchings, then we know that for any component, suppose this K1 component only has odd number of vertices, then we know for sure that at least in this component, there will be, if you just consider the edges inside this component, there will be at least one vertex which will remain unmatched in this component because there are odd number of vertices and like in a matching, always even number of vertices get matched. So there will be one vertex which will remain unmatched in this odd component. Similarly, like for any odd component, there will be at least one vertex which will remain unmatched. And then maybe that vertex can get matched with the uh, uh, maybe that vertex can actually get matched with like a, a vertex in U or something like because there's one unmatched vertex, and then maybe the only way it can get matched is with a vertex in U in the set U. And similarly, like for all the odd components, the that vertex can get matched with a vertex in U. So essentially, like what then happens is then there are like in this component U, there are like U minus uh, like odd number of odd components in the graph G minus U. This number of vertices left, which are needed to be matched to each other, and actually can and then actually what we can show is this kind of a thing that the size of any maximum matching will be like less than equal to minimum of for all the sets U. The for any set U, the maximum matching will be less. The size of maximum matching will be less than equal to half times the number of total number of vertices in the graph plus U minus number of odd components in the graph G minus U. And the core idea behind this is just what I just said, that in one of the odd components, what's going to happen is at least one of the vertices is going to remain unmatched, and then maybe it gets matched to a vertex in U, in the set U, and similarly for all the other odd components, this is going to happen. And what this kind of says is like the size of any matching will be less than equal to uh, this value, half times the number of vertices plus this is usually called the excess of the vertex set U. The value U minus O of G minus U is usually called XS. So half times V plus XS of the graph, uh, uh, the size of any matching will be less than equal to this, and so it's actually less than equal to minimum of all of this. And this is essentially the idea is because these number of vertices will actually always remain unmatched in the graph. Yeah. Yeah, because like if there are like more odd components than like the number of vertices in U, then this will be the quantity which remains unmatched. And so if this is the quantity which remains unmatched, then at most like V minus this quantity will get matched. So V minus this quantity will be just V plus U minus O of G minus U. And so uh, at most this many vertices can get matched. And so size of maximum matching will be less than equal to half the number of the vertices which can get matched. So yeah, so this is one side of the inequality which is pretty clear. But like what Turdberg's theorem says, it can be also analyzed in terms of blossoms and all. So shown in the lecture that actually this inequality is actually tight. That size of maximum matching, this is actually equal to this quantity, the minimum over all the sets U, the value half of V plus U minus O of G minus U. So this side is kind of trivial or like easy to see. The other side, like which shows that this is also greater than equal to. Like, so that it does not equal like so showing this less than equal to is not too hard. Like we just discussed this on a very high level right now. But the non-trivial part is actually showing this inequality, this equality, like which is pretty interesting. So yeah. So this is what Rydberg's theorem says. So this can be seen as a like a nice equivalent to like the Hall's theorem. So Hall's theorem is for bipartite graphs. Here, this Rydberg theorem is a generalization of Hall's theorem to any arbitrary graph. So yeah, and you can actually like see that if you consider the graph to be bipartite, this can be a homework. That this Studworth theorem, in case of bipartite graphs, just reduces to the Hall theorem. So yeah, maybe you can try it yourself, or maybe let's just leave it at that. But you can try it yourself that given the Studworth theorem statement, this is equivalent to Hall's theorem in case of bipartite graph. Try to prove this yourself. It's not too hard. Trust me. Okay, then I guess yeah, this was these were the topics which was like so quite a heavy quite a lot of topics related to graph theory were discussed in first 2 weeks. So quite a bit of heavy machinery which was discussed, which is like really useful even till this day in graph theory. These concepts of blossoms and like these augmenting paths and all have found uses even in very recent research. So yeah, very important thing. Okay then. So after this, since we have some time left, maybe I'll go over like summary of some other weeks also. Like, but the summary so till now we had a bit more in-depth discussions for week 1 and 2 because we did not have any problem solving session. But now for week 3 onwards, so maybe we won't discuss for all the weeks because we have had like lecture like problem solving sessions very recently. So maybe for the first half only we'll be doing a summary. So we'll do a summary for the first 6 weeks only. So week 1 and 2 we have done. So let's just try to summarize or like let's just remember like the topics which we did for week 3, 4, 5, and 6. So yeah, we won't be discussing any definitions in detail, but I'll be just going over them very briefly. Because anyways, whenever we had these problem solving sessions, we already had these summary notes at the start of each session. So yeah. So okay, so after all of this was discussed related to matchings and flows in graphs, in week 3, there the lectures in the lecture videos started introducing the concept of randomized algorithms. So what are randomized algorithms? Randomized algorithms are algorithms which use randomization to give us some good outputs. For example, Kargar's algorithm for min-cut, which we discussed right now, was a randomized algorithm. And some further use of randomized algorithms were discussed, like the what is polynomial identity test. So, like randomized algorithms are used for polynomial identity testing. So, first of all, what is a polynomial identity testing? So, suppose you are given uh, you are given a polynomial, uh, uh, you're given a polynomial formula, and then you have to answer whether it is or like you are given, let's say yeah, so you're given a black box access to a polynomial formula that you can substitute values for the variables in the polynomial, and the black box will give you what does the polynomial evaluate to, and then what you have to answer is like uh, like is this polynomial identically zero or not, using some queries, using some black box queries. This is called polynomial identity testing. So yeah. Uh, and designing a deterministic algorithm for polynomial identity testing has there's no we don't know any deterministic algorithm which does this in polynomial time. Uh, so this has turned out to be quite challenging, the polynomial identity test, a deterministic algorithm for polynomial identity testing, because whatever deterministic input you give to your algorithm, it might actually be that the original polynomial is a non-zero polynomial, but your specific input was a zero to that polynomial, and there can be like infinite number of zeros. So whatever you input you give it, it might be that for that specific input, it turns out to be a zero of the polynomial. So polynomial identity testing is finding a deterministic algorithm for a PIT. Polynomial identity testing is also called PIT. Is kind of has proven to be quite a challenge, but turns out there exists a very efficient randomized algorithm for this, which is just okay. Instead of putting all of these deterministically, the input values deterministically, just choose these input values uniformly at random, any uniformly at random value, and it can be shown using it can be shown that with very high probability it will be that if the original polynomial is a non-zero polynomial, then uh, your output will also be a non-zero. Like the black box will evaluate a non-zero value. for your specific uniformly random input. And this is like formalized by Schwarzschild lemma. So you can see the exact statement of Schwarzschild lemma, but it essentially says this only, that if you uh, if you initialize the values randomly, then with very high probability a non-zero polynomial will evaluate to uh, uh, non-zero value. So yeah, and this has a lot of applications. For example, there are applications of PIT for perfect bipartite matching. So we write a adjacency matrix for the bipartite graphs in terms of polynomial. Uh, and then we try to find out if it was shown in the lecture that if the determinant of that is non-zero, then actually there exists a bipartite matching. If it is zero, then it is not a bipartite matching. If if the determinant leads to a non-zero polynomial, then there is a perfect bipartite matching, and if the determinant leads to a zero polynomial, then there does not exist any perfect bipartite matching. But evaluating whether this is polynomial is a zero polynomial or non-zero polynomial, you cannot express the polynomials by themselves because they can be very large, but you can initialize the values for each of the randomly initialize the values for each of the variables and check whether the determinant initialized at those values is zero or non-zero. And this gives us an algorithm, a randomized algorithm for perfect bipartite matching. And this can actually be generalized to maximum bipartite matching also. So this was, I don't think, discussed in the lecture videos, but we discussed this in our problem solving session. That instead of checking whether determinant is zero or non-zero, so determinant is non-zero, essentially it says that the rank of the matrix which you constructed is n. Essentially, where n is let's say the number of vertices on one side of the bipartite graph. So essentially, what it essentially says is one other way to think about it is like the rank of the matrix which you constructed is actually equal to the size of the maximum matching of the graph. So, and if determinant is non-zero, then rank is n, and that's why you obtain a perfect bipartite matching. And actually, it turns out this statement is true, for uh, like uh, uh, like for maximum bipartite matchings also. So just initialize that matrix with random values, the matrix corresponding to the bipartite graph, and if there exists uh, rank R, if the rank of this matrix is R, then there exists matching of size R, and that will be the maximum bipartite matching. So yeah, so rank of the matrix is equal to size of the maximum bipartite matching. So this is a very nice application of polynomial identity testing. And then there was an introduction to randomized quicksort, where we select the pivot at random, uniformly at random, and then it was shown in the lectures that yeah, with very high probability using this, we will be able to obtain like like the runtime of the algorithm will be with very high probability n log n only. So yeah, in randomized quicksort we choose the element uniformly at random, and yeah, uh, the pivot uniformly at random around which we like uh, like uh, move around the elements of the array. Like small element smaller than pivot go to the left side of the array, element larger than pivot go to the right side of the array, and then we recursively apply quicksort. And it can be it was shown in the lecture videos that yeah, uh, mm, this thing takes order n log n time with high probability. And then there were discussions about concentration inequalities. So what are concentration inequalities? Concentration inequalities are essentially uh, give us an idea of how probability given any random variable and its probability distribution, how does the random variable behave? Like with or how does the probability distribution behave around its mean, around its expectation value? For example, like for example, if we are given a random variable and we are also given its expectation, then one would expect that most of the probability mass should be concentrated around the expectation only. Uh, and this is what the concentration inequalities kind of formalize, and these are kind of like there are many concentration inequalities like but ones we discussed were like these are like some of the most basic ones, and like the Markov inequality. This is true for any non-zero any non-negative random variable. Then like where we just see the constant, we just apply the constant inequalities for like checking the probability mass of the random variable around its expectation or something. And then there is the Chebyshev inequality, which also takes into account, along with the expectation, the standard deviation of the probability distribution. And then and then comes the Chernow bounds, which are even more like specialized in nature. So Markov just deals with arbitrary non-zero random variables and their expectation. Chebyshev deals with like arbitrary random variables, but also takes into account their standard deviation. But Chernow specifically works for like uh, some of Bernoulli random variables. So like just 0 1 random variable. But still, it's a very, very powerful inequality. Chernow bounds are used a lot in like in proving a lot of algorithms. So yeah. So Chernow bounds, yeah, they are more specialized, but they are also used a lot. And we saw also many uses of the Chernow bounds. Yeah. And then in week 4, actually, we saw these applications of concentration bounds for the first of all the coupon collector problem. So coupon collector problem in a nutshell says that okay, if you have n coupons inside a box and you pick one coupon uniformly at random in every try, then in how many tries uh, will you be able to see all the coupons at least once? And it can be shown that with very high probability, using the concept of Chernow bounds, it can be shown that with very high probability you can see all the coupons numbered from 1 to n in about n log n tries. So if you repeat this trial, if you like look at a coupon randomly, approximately n log n times, or like 10 n times n log n times, then you would have seen each of those coupons were numbered from 1 to n at least once. And then there was this birthday paradox. The birthday paradox is that, yeah, if there are uh, uh, if there are like n days, let's say in a year, like we know the n is 365, but let's say an arbitrary year has n days, then if you mm, if you take about like uh, root n students, if you take a room of size root n, uh, if you take a collection, if you take a set of students of, so suppose if a classroom has size approximately of root n students, then at least two students will share a birthday. Uh, just a second, guys. I'll have to mute myself. Yeah, sorry for this, guys. So yeah, so birthday paradox essentially says that if there are n days in an year, and if you take a uniformly random set of students of like size root n, then actually like at least two of the students will share a birthday. And this is kind of a paradox because deterministically, actually, you can have like the minimum number of students which you need to ensure that at least two students share a birthday is n plus 1 by the pigeonhole principle. But if you take the students uniformly at random, like if from the whole, like, like, uh, uh, or like essentially you say that, yeah, yeah, that in a class, like, if you assume that every student's birthday is a uniform random variable, like it occurs on either day 1 till day n, like uniformly random from 1 to n, then the probability that, like, it's with very high probability, if you take root n students, at least two students will share a birthday. So this is kind of a paradox, like, because deterministically it might be n plus 1, but if you take this uniformly at random, the assumption of uniformly at random, then it's like root n. And then there was a balls and pins example. Uh, which was again like a very similar problem to like a coupon collector problem, like where you say that like yeah, you are throwing balls into the bins and then like how many balls, like you are throwing a ball randomly into the bins, then how many balls do you have to throw? Like if there are like if there so that like every bin has at least one ball or something. Yeah. So and then there was discussions about 2-point sampling. So what is 2-point sampling? So for suppose there exists any so on a high level, like suppose there exists any randomized algorithm, so it has to utilize some amount of random bits. And if you are using that randomized algorithms multiple number of times, then each time you are taking some random samples and all. So you are increasing the randomized bit complexity. So you need more random bits if you want to do a lot of rounds of sampling. And like sometimes obtaining these random bits is costly. So what if we want to minimize the like we want to reduce the number of random bits which we need to use? Then this 2-point sampling actually says that, oh, you don't need to, if you are doing like let's say 10 rounds of sampling, then you actually don't need 10 you don't need to sample uniformly random bits 10 times. You can just sample them at 2 times, and then these two random samples can be composed in some manner so that you always have like in every time you have a like random uh, bit with you. So instead of like sampling 10 times, you can actually just sample 2 times, and still your algorithm can follow. Your algorithm will still have the same kind of uh, uh, probability guarantees. So this is what, so this 2-point sampling is really useful to reduce the randomized bit complexity of any algorithm. So yeah. And then there was a discussion about a randomized algorithm for two-set problem. So yeah. And then in week 5, we discussed the concept of Markov chains. What are Markov chains? So they are used to model random processes. And like we also discussed about mixing times of Markov chains, fundamental theorem of Markov chains, a lot of definitions related to Markov chains. And then there was a discussion about the coupling lemma. Coupling lemma is nothing but like with any two probability distributions, coupling lemma says that the total variation distance between the probability distributions is less than equal to the probability that the two variables are not equal to each other. So if the two variables are x and y, then total variation distance between x and y is less than equal to probability that x is not equal to y. And the proof of this was not difficult, but yeah, it's a very useful lemma, coupling lemma. And then there were some applications of Markov chain, like the random walks on undirected graph, cycles, and so on. So yeah. And then in week 6, uh, uh, we discussed like some Monte Carlo methods, um, like where we use these kinds of tools of randomizations to uh, uh, estimate certain values. We use randomizations to estimate certain values, which might be difficult to estimate otherwise. For example, we saw how can we estimate pi using Monte Carlo method. Like if you remember, just we drew a square and then a circle inside it, and then any uniformly random point in the square will lie inside the circle as well with probability pi over 4 or something. And using that, using sufficient number of samples, we can actually estimate pi to a good approximation ratio. And then we also discussed mm, FPRAS for DNA counting. What is FPRAS? Fully polynomial randomized approximation scheme. Uh, so given a DNF instance, if you want to find out, so DNF counting is given a DNF instance, find out the number of satisfiable assignments. And note that this problem, exact problem, is NP hard, like because DNF counting can be used to solve uh, satisfiability problem, and that's why it's NP hard. But we can give a good approximation to it using the FPRAS, which was the Monte Carlo method. And then we also discuss about like instead of like suppose we also don't have access to, so till now we assume that we have access to uniformly random samples. What if we don't have access to uniformly random samples? Like then can we have like approximately uniform random samples? And then there was like the concept of approximate sampling, which was like fully polynomial approximate uniform sampling. And how can we do this and what are its uses? So this was used in like this FPAUS was used for counting number of independent sets because we cannot like fully uniformly at random estimate find the independent sets, but we can like have a uniformly like approximate uniformly random sampler for independent sets. And then we can use Markov chain Monte Carlo methods to first obtain these approximately uniformly random set sampler for independent sets, and then it can be used for counting number of independent sets. Like we use these uniformly random samplers for DNF counting. Similarly, these approximate uniformly random samplers can be used for counting independent sets. Why use approximate samplers? Because it's not we cannot obtain uh, 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 exact uniform samplers for independent sets. But turns out like approximate uniform samplers also suffice. So yeah. So this was all which was discussed from till week 6. Like so of course like we did not discuss any of these in detail, but I hope I gave like sufficient uh, high level background of whatever was discussed, so that can act as a like quick revision for you guys. If you need to look into any detail, then anyways you have the lecture notes and also the notes of the problem solving session. There also we usually have in all the solving sessions we first discuss whatever was discussed in the lecture videos on a high level and then proceed. So you can see them also if you want to go over any of the concepts. Or of course the best thing is if you have time you can go over the lecture video. But yeah. So, okay then, guys. I guess this was it from my end for today's session, for this today's last summary session. And yeah, I had put aside some time, so we still have like 10-15 minutes left. I had put aside this time so that if someone joins the session in person and has some doubts, I can clear those doubts. But I guess no one is really present in the session. So maybe I'll just wait for 5 minutes. If anyone joins the session and has some doubts, then maybe I can try to answer those doubts. But if no one else joins in, like let's say the next 5 minutes, we'll close the session. So I'll just mute myself till then. Okay, I guess since no one has joined the session, we can uh, close the session. So once again, like since this was the last session for this semester, so thanks a lot to everyone who is watching on YouTube. So yeah, since it's the last session, yeah, all the best to you guys for your final exams. And yeah, hopefully I'll see you guys next semester in some other course. So yeah, goodbye then. Thanks a lot for watching, guys.